Well, now we're going to use Taylor's inequality to prove that sine of x is the sum of its Maclaurin series for any value of x. So remember, the Maclaurin series for sine of x, centered at 0 of course, is the alternating sum x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, etc., etc. I would like to show that for any value of x, that this series converges to sine of x. In other words, I want to show that sine of x minus the partial sum Tn of x goes to 0 as n tends to infinity. So I want to show that the limit as n goes to infinity of the absolute value of this remainder is equal to 0. What does Taylor's theorem about the remainder tell us? Well, remember that we saw there was an upper bound on the absolute value of the derivatives of sine of x. They're all less than or equal to 1. So no matter what n is, we get the absolute value of the n plus 1th derivative at x is less than or equal to 1. And Taylor's theorem tells us that the absolute value of this nth remainder must be less than or equal to the absolute value of x to the n plus 1 over n plus 1 factorial, no matter what x is. Well, looking for the limit as n goes to infinity of the absolute value of Rn of x, we know it has to be greater than or equal to 0 because it's an absolute value, and it must be less than or equal to the limit as n goes to infinity of the absolute value of x to the n plus 1 over n plus 1 factorial. However, we saw earlier that this limit equals 0. This was the very important limit we pointed to when we saw that the series, the sum of x to the n over n factorial, converged. So now, since the limit as n goes to infinity of the absolute value of the remainder is between 0 and 0, it has to be equal to 0, and therefore we can conclude that whatever the value of x is, that the remainders sine of x minus the partial sums of the Taylor series go to 0 as n tends to infinity. Therefore, the Taylor series must converge to sine of x. So, whatever the value of x is, sine of x equals the sum of its Maclaurin series. It equals the sum from 0 to infinity of minus 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial.